good morning, everybody. So thank you very much for the great introduction. So it's my great pleasure to be here today. Actually, the main purpose of my visit here is actually we have a workshop tomorrow and the day after tomorrow. So we will bring 16 people from weekend and we have 2-day workshop here. So that's something we discussed for many years and finally we made it. But then I asked Ben whether I can give one more talk before the workshop. So this is the one today, and thank you very much for arranging the talk today. So as introduced already, I'm from RIKEN and University of Tokyo. So I'm director of RIKEN Center for Advanced Intelligence Project. I have actually a few more slides about RIKEN, so let me talk about RIKEN later. Then I'm also a professor at the University of Tokyo, so doing computer science. And I'm also supporting some local startups in Tokyo because we have many good people also in industry. It's quite important for us. Okay. Then my research background is basically machine learning theory and algorithm. I'm very interested in fundamental research like machine learning in non-stationary environments, density ratio estimation, reinforcement learning, variational Bayesian. Then more recently, some machine learning from weak supervision. So when I work on one topic, I try to spend 10 years and then try to publish a book. So far we have 6 books. One is textbook, so we 5 books on our research. Then potentially, I'm also very much interested in machine learning applications because my background is in engineering. But nowadays, application of machine learning is even more challenging because we need a lot of data, a lot of resources. So it's quite impossible for us to pursue application research by ourselves. So we decided to basically focus on basic research in our team. And we try to have collaborators outside in industry or other research centers to explore interesting applications. So I was so lucky to be involved in those applications. Then I'm also quite active in academic activities. And I was a program chair for New RIPS, AI Starts, and Asian Conference on Machine Learning, SML. This is something we started 15 years ago. Then also I gave a keynote talk, iClear 2 years ago. So this was really a memorable event. And it was the first machine learning conference, big machine learning conference held in Africa. So it was held in Rwanda. So it was really a nice experience for me. Okay, then so about RIKEN. So I'm from RIKEN, and what is RIKEN? So in Japanese, so we use 6 letters for our center. And this is pronounced as Wikagak Kenkyusho. And the first 3 characters means physics and chemistry. And the last 3 characters mean research institute. So then some years ago, so RIKEN in English was called Research Institute for Physics and Chemistry or something like that. But now, so RIKEN is beyond physics and chemistry. We have biology, medicine, supercomputer, AI. So they have to change the name, but we can't really change the full name. Then, so here comes the Japanese acronym. So 6 letters are too long usually. So people take the first character and 4th character and attach them. So this is in Japanese pronounced as RIKEN. And basically ordinary people call us RIKEN. So nobody calls us Wikagak Kenkyusho because it's shorter and more convenient. Then at some point, RIKEN headquarters decided to use this Japanese acronym as our official name. So this means RIKEN is no longer an acronym of something, not Research Institute for KEN, but it's our official name. So RIKEN. Then RIKEN actually has a really long history. So started in 1917 as a private foundation actually. So actually Emperor's family also donated some initial funding. So then after that, so RIKEN was so successful in physics and chemistry research. And in 1939, so they had 63 companies and 121 plants. And RIKEN was called RIKEN Concern. It was really a big entity, quite successful. But because it was so successful, so after the World War II, so unfortunately RIKEN was broken up. But then in 1948, so RIKEN restarted as Scientific Research Institute, and then it became a public corporation. After that, so we had 2 Nobel Prize laureates in physics, and also one of the previous president was Nobel Prize laureate in chemistry. Then nowadays, so we are called National Research and Development Institute, and we are fully funded by the Ministry of Education. So then this is the organization of RIKEN now. So RIKEN actually has a 7-year research term, and the new 7-year term just started in this April. So this is really a brand new organization. So in total, Weekend has more than 1,800 researchers, and we have 4 research domains. So they are physical science, sustainability science, life science, and mathematical, computational, and information science. And we belong to this last one. And our center, so Center for Advanced Intelligence Project, is included here, AIP. And what is RIKEN AIP? So RIKEN founded the Center for Advanced Intelligence Project in 2016, so under the Ministry of Education, Culture, Sports, Science, and Technology. And we have now 137 employed researchers, and more than 40% are international researchers, and about a quarter of them are females. Then we have more than 250 visiting researchers from industry and university, domestic universities mainly. Then we have about 100 domestic students. Then we have actually quite a lot of international interns, so close to 200 students in total so far, and some are also from Australia, and they are quite active. Then, so our office is located in the center of Tokyo, so 10 minutes walk from the central Tokyo station, and we are located on this building, 15th floor here. And inside we have a nice room, like this. And we have a visitor workshop in this room. Then actually we have many teams. So some teams are in this central office in Tokyo, but many other teams actually belong to universities, different universities. So our offices are also distributed from Sendai to Nagoya, Kyoto, Nara, and Fukuoka. So we have many teams distributed across the entire country. Then, so this Weekend AIP project was actually originally designed for 10 years. And this is actually the final year of the first AIP project. But as I said, the Weekend has the 7-year term, and new 7-year term has just started from this April. And we are already in the second term. And this means at least we have 7 more years. But maybe already our center is a kind of permanent center, so we can continue doing AI research for a long time. So hopefully through this talk and through the workshop tomorrow and the day after tomorrow, we can discuss more longer term collaboration plans. So that's the main purpose of my visit today. Then, so in Weekend AIP, we have 3 research groups. The first group is called Generic Technology Research Group. And here we have 16 teams. They are working on fundamental topics like machine learning and inference algorithm. And also some people are working on more theoretical topics like statistical learning theory and optimization theory. And the second group of researchers teams are working on called goal-oriented technology research group. And they have 2 subgroups. And so one is for AI for science. So they are supporting AI research. They are supporting scientific research in cancer, material science, genomics, etc. So these are quite active in Japan, and we are supporting their activities. Then in the second half, so they are working for societal problems in Japan. So we are public institute. Of course, we do some more business-like research collaborations, but at the same time, so we work on societal problems like natural disasters in Japan. So we have a lot of earthquakes, tsunami, typhoons. So we are working on these things. Also, elderly healthcare. So this is an urgent topic in Japan now. And also, we are working on robotics. So it's a new project we started recently. Then the last one is AI in Society Research Group. So the first 2 groups are more on the science and technology side, but the third one is more on the society side. And they are working on personal data management, AI security, economy and management, ethics and governance. So all 3 groups having completely different backgrounds, and we have quite a lot of diverse people. But we put them together in the same institute, and we are collaborating together. So of course, still there are a lot of challenges to have fusion of these different topics. But we are making a steady progress in the last 10 years, and hopefully we continue this kind of nice culture in the next 7 years at least. Okay, great. That's about Weekend, and let me talk about my main topic, reliable machine learning. So nowadays, the reliability of machine learning systems is quite important. So because we already use machine learning systems in many applications in society. But still, those machine learning systems suffer a lot. In particular, some uncertainty behind. For example, so our training data, so machine learning systems are trained based on data, but the data can contain only insufficient information for training the system. So we call it weak supervision. Still, so only from weak supervision, we want to guarantee that our system is kind of reliable theoretically. So that's one main challenge for us. Then, so we have a lot of data now, but those data are usually labeled by human or some sensors automatically. Then they are prone to the error. Still, we want to guarantee that our system is somewhat reliable. And the last one is data bias. So world is changing over time. So the data collected today may not be really useful tomorrow or the day after tomorrow because world is changing. But still, we hope to somehow extract some essential information from the data today and guarantee that this is still useful tomorrow and the day after tomorrow. Or, so same thing. So we are not allowed to collect data as we want because of some privacy concerns. So then, so from the testing viewpoint, so our training data is somewhat biased because of this privacy concern. So then actually mathematically it's the same issue as the changing environment. So our data is biased compared to the test data. So then we want to somehow mitigate the bias issue. So that's a challenge here. So we are interested in these basic topics for reliable machine learning. And today I try to give an overview of these three topics. And then so we talk about our current and future challenges. Okay, then, so let me start from the first topic, weakly supervised learning. So nowadays, so supervised machine learning is quite successful in many application domains. And typically like speech recognition, image understanding, language translation. So these are so trained in a supervised learning way. But they need big label data. But in many other application domains, unfortunately, so big label data is not always available. Like in our Riken Center, so we are interested in medical research, natural disaster research, robot research, so brain science, etc. In those domains, so big label data is not available. We have a lot of earthquakes, but still it's far from big data. So somehow, so we want to guarantee the performance of machine learning, even in these challenging applications. So this is the main challenge. And what I want to really say is, so okay, we want to train a machine learning system only from small data. But unfortunately, learning from small data is not theoretically possible unless we have strong prior knowledge or some domain knowledge. Instead, so we decided to use still big data, but those big data may only contain some weak supervision. That doesn't contain strong enough information, but still we want to guarantee that big enough weak supervision we can guarantee. That's our approach. And here's one example. So it's called positive unlabeled classification. And we consider still a binary classification problem. It's the simplest problem. So given a sample, we want to classify it to the positive class or negative class. So that's the simplest machine learning problem. But in this PU classification problem, so we still observe positive data, but we can't observe any single negative data. Like in principle, there exist red points here, but those red points are not observed. But instead, we observe so-called unlabeled data, so these black points. So these unlabeled data are basically a mixture of positive samples and negative samples, but we don't know which one is positive and which one. So still unknown. That's why it's called unlabeled. So then the task is, so given blue points and black points, still we want to separate blue and red. So this is a problem called PU classification, positive unlabeled classification. So here's a textbook example of this PU classification. So it's advertisement clickbait. Suppose an advertisement appears on screen, and suppose the user clicks it. Then this is the positive sample that the user likes. So then we can collect positive data, the blue one here. Suppose another advertisement appears on the screen and not click this time. Then naively, we want to regard it as a negative sample because the user didn't click it. But actually, this is not always true. So the advertisement was not clicked because user didn't like it, or user liked it, but he or she didn't have time to click it. Another luckily unclicked advertisement are still unlabeled. So it could be either positive or negative. So then those are black points, basically. But still, we want to predict whether the next advertisement you click is interesting or not. So positive. So then the task is really PU classification. Blue and black points are only observed, but still we want to predict blue and red. So this is a PU classification. And I have actually 2 slides for technical derivation, and let me just quickly go through it. So it is actually standard. So in the standard way, so we define the classification risk in this way. We consider pointwise loss function. Then this loss function is expected over all entire distribution. This is the classification risk that we want to be. Then we decompose this classification risk into the positive part and negative part. Then in the standard supervised learning case, we have both positive data and negative data. Then, so these 2 terms can be naively estimated from data. And in this PU classification scenario, we don't observe negative data. So estimation of the second term is actually an issue. So then here, pi is the classifier, and this is something we also have to estimate from data. But today, so for simplicity, let's assume this is no. But in practice, we also have to estimate it from data, PU data. But there's a series of papers working on this estimation problem, and we just use one of them. Then the second term, so this is R minus now. So we want to estimate R minus without using negative. Yeah. And here's a very simple trick. So we know that unlabeled data density, P of X. So by definition, this is a mixture of positive data density and negative data density. And the mixing coefficient is pi and 1 minus pi. Like we have positive data density, blue one here, and negative data density, red one here. Then unlabeled data density is this black dotted one. But these are a mixture of these 2 densities. Then we just use this relation to eliminate the expectation over negative samples. So now R minus can be expressed in 2 terms. The first term is the expectation over unlabeled data minus the second term. So this is the expectation over positive samples. Then these 2 can be estimated from positive and unlabeled data. Then finally, we have an unbiased risk estimator that can be computed only from positive and unlabeled data. And we just minimize it by backprop or whatever. So this is the basic solution to this classification problem. Still, this basic solution does not work well in practice. So we need one more trick to make it work in reality. So what we have done so far was to re-express this R minus into 2 terms, and so the difference of 2 terms. And we estimated these 2 terms separately from unlabeled data and positive data. Then suppose loss function L is non-negative. So this is often the case in reality. So then, so by the definition of R minus, so entire R minus is also non-negative, just the expectation of the loss function. Then, so this R minus is non-negative. But now, so let's say this is 3. Then, okay, 7 minus 4 is 3 or something like that. But now we don't know 7 and 4. The 7 and 4 are estimated from data independently. And 7 can become 5, and 4 becomes 6 or something like that. Then 5 minus 6, and this R hat minus can be negative. It is minus 1. So this is actually a problem. So because of this negative term, so even though R minus is non-negative by definition, this R hat minus can be negative. And this actually causes a big problem. So here's a simple experimental result that we did. So neural network training over stochastic gradient. Then, so in the standard supervised learning case, PN learning, so this blue dotted line, the training error decreases like this, it converges to 0. Then the test error also decreases like this, it converges to 3. So that's the standard case. Then in PU classification, so suppose we use this one as the training criterion. But then this red dotted line, it goes down quite quickly, and at some point it becomes 0 and it goes negative like this. Then the test error, this red solid line, it goes down faster, it decreases like this. So when the empirical error, the training error goes negative, so the test error started to increase like this. It's a clear indication of overfitting. So we wanted to avoid this problem. And one of the simplest approaches is this non-negative correction. So once this r hat minus becomes negative, it is rounded to 0. Simple correction. But okay, this simple correction works quite well. So now, this yellow dotted line, the training error is kept non-negative like this. So because of this max 0 operation. Then interestingly, the test error is also kept lower. Then in the end, it works quite well. We can avoid over. So these two are basically our important recipes. So we first estimated the classification risk only from available data. This is one recipe. Then the second recipe is non-negative correction. So once the empirical risk goes negative, we correct it max 0 operation. So these two are essential contributions in this field. And later we show that this is quite universal. But before going into that, so let me show one example of PU classification. So it's signal enhancement. The task is quite simple. So given noisy signal, we want to remove noise and have a clean speed. That's a problem here. And to do so, usually people use so-called parallel training data. The parallel training data means for the same signal, they have a noisy version and noiseless version, clean version. And by comparing these two, so they can train basically neural network. This is what people do in reality. But in practice, so collecting such parallel training data is so difficult. So then usually, they invite the subject to a clean, nice studio and collect record clean speech. Then for this clean speech, they add synthetic noise. So by that, they have a parallel training data and then train the system. But as usual, such synthetic data always does not work well in reality. It doesn't generate so well. Then in our case, we just use PU classification. So first, we put the microphone in some noisy environment and just record noise. And this noisy information is always positive samples for us. Then we ask somebody to come to the noisy environment and just speak. So then we observe the mixture of noise and speed. And once we apply a Fourier transform, so this is actually a mixture signal in speech and noise and speed. And for us, this is actually unlabeled data. So we basically perform classification in the time frequency domain. So then, for each patch, actually, we perform classification. Then, pure noise is a positive sample. And this mixed signal is actually unlabeled data. Then this is actually enough. So we can train a PU classifier only from pure noise and noisy speech. Then we can separate speech and noise without really observing clean speech. Of course, if you use fully supervised data, the performance is better. But with our approach, without having clean speech, we can actually achieve close performance to the supervised learning case. And this was selected for the best paper award at ICASP 2 years ago. Okay, that was about PU classification. Then, as I said, our recipes are quite universal, and we can apply the same techniques to many different weakly supervised learning scenarios. And let me explain one more problem here. So it's called UU classification, unlabeled classification. So this is one of the most challenging cases. So we don't observe any labels in this scenario. Instead, we have two sets of unlabeled. And our assumption is that, we know the class proportions, and class proportions are different. Like in the first data set, so let's say we have 60% positive and 40% negatives. We don't know which one is which, but we know the ratio. Then in the second data set, let's say 20% are positive and 80% are negative. Yeah. Then only from that information, so we can train the classifier with guarantee. So essentially, we can apply the same technique as PU classification. Then we obtain the solution. So our hypothetical application of this UU classification is medical imaging. So suppose we have some medical imaging. We want to predict whether cancer exists or not. Then, okay, let's say there are 2 hospitals. Then, okay, each hospital has a lot of medical images. But as usual, the medical doctors are so busy, so none of them are annotated. We are all annotated. Suppose we have some prior knowledge that in hospital A, so let's say 20% of the patients are cancer. then hospital B, 30% of the patients are cancer or something like that. Then in principle, only from that information, we can train a classifier. And given the new medical image, we can predict cancer existence without having any single annotation. So that's the power of UU classification. And then we have many more interesting domains. Also, this can be extended to multi-class problems. So today I don't go into the detail. We have a lot of multi-class weakly supervised learning problems. Then altogether, so we put all the mathematical frameworks into a single book published from the MIT Press 3 years ago. But this was already done 3 years ago, and we also made a lot of progress in the last couple of years. So we had mathematically unified framework for weakly supervised learning and new weakly supervised learning problems and new algorithms. And also we had nice applications in imitation and large pre-trained models. Like imitation learning is one of the important branches of reinforcement learning, like training a robot control system or computer games. But then like learning from reward function is actually not that straightforward, or designing a reward function is not straightforward. And people try to provide a demonstration to learn reward. Suppose we consider robot arm reaching task, like grabbing something. Then, so we basically guide the robot hand to like reach the object. Then we just repeat this one many times. Then we can collect like some demonstrations, and then we can perform supervised learning to learn the reward function. But collecting such demonstrations are also is quite expensive. So here we can naturally use weakly supervised learning, and we can have a good performance in imitation learning scenarios. Then, so large language models and visual models. So we have a lot of large pre-trained models nowadays. But those like generic foundation models are often fine-tuned using downstream data nowadays. So then this like fine-tuning part is basically supervised learning. And we can naturally replace this part with weakly supervised learning. So we only have weak supervision from downstream tasks. But still, we want to fine-tune the original foundation model with some guarantee. So that's the idea here. So we are still making a lot of progress. Hopefully, I have another chance to report new results in the near future. Okay, that was about weakly supervised learning and the longest part. So the second part is quite short. So it's about noisy label learning. So in this project, we are considering a kind of quite standard supervised learning problem with noisy output. Like in the case of regression, so let's see one-dimensional regression in this illustration. So we have input X on the horizontal axis, output Y on the vertical axis. But instead of observing X, Y, so this time we have X and Y bar, noisy one. So points are noisy. But still, usually we don't care. We just minimize some loss function, like squared loss or something, then obtain a solution. So that's a standard practice. And similar in classification. So originally, so data here are all class 1, class 2, class 3. But because of some label flipping, so we have some mixed labels like this. But again, usually we don't care. So we just collect big data and just minimize the loss. And we believe that okay, big data helps. It should work well. And is this really true? So for regression, maybe yes. So we need some assumption that noise is mean zero and additive noise. Then, so basically noise is cancelled out automatically. As long as we have big data, big enough data, so our solution is good enough. But unfortunately, in the classification case, like label flipping is, then, so it's not true. Even if we have big data, so there is a possibility that our solution is still quite biased. So actually, we need a specific noise reduction mechanism to achieve consistency. So consistency means we have a large number of samples, so our solution converges to the best one. So to guarantee this property, we need specific noise reduction mechanism. So this is such a simple fundamental problem, but it was not completely solved yet. So that's why we have been working on this topic. Then, so to approach like noisy data, so in classification, a standard approach is to consider so-called noise transition matrix. So it's T here. So this basically represents the probability of flipping clean label to noisy label. like in the case of 3-class problem, we have a 3x3 matrix like this. And this is noise transition matrix. Then based on this T, so 2 approaches are proposed. So one is to adjust classifiers by T transpose to simulate noise. So T is basically a noise matrix. So by applying classifiers output to T transpose, we can basically simulate noise. Then now we have a noisy classifier and noisy labels. Then just learning, fitting noisy classifier to noisy labels, we can somehow maintain. And the second approach is loss correction by T inverse. So T is a noise process, and T inverse is a kind of denoising process. And if we apply a vectorized loss function to T inverse, we can basically eliminate the influence of noise, and we can still obtain an unbiased risk estimate. So these are quite systematic and kind of systematic approach, quite nice. But we need to estimate T only from noisy data because T is not available. This is actually the most challenging part. And that's why we spent more than 5 years to estimate T only from noisy data. And we have to say that estimation of T only from noisy data is actually a mathematically not solvable problem because the solution is not identifiable. So we need some additional condition or information to make it estimable. So that's why we spent many years to somehow formulate the problem nicely. Then finally, we had one good solution that can estimate T under weaker conditions. So let me spend one slide to explain the method behind. So the method is called volume minimization. So for illustration purposes, let's consider a 3-class problem. So T is a 3x3 matrix, and we consider a triangle here. So each vertex consists of corresponds to 1, 0, 0, 0, 1, 0, 0, 0, 1. Then, the noise transition matrix 2, 1 forms a simple triangle, inner triangle. First row, second row, third row. And if there's no noise, T is an identity matrix. Then it agrees with the true outer triangle. But generally, they are included in the outer triangle. Then, interestingly, noisy training data, X and Y bar, they can be mapped in this inner triangle, like this. But by definition, actually, they live inside this triangle. We don't know this triangle, but those points actually belong to the inner triangle. Then, based on this observation, our algorithm is quite simple. So we consider some initial triangle like this. And first, we try to include all training point, noisy training data inside. So this corresponds to loss minimization. Then the second term, we try to shrink the volume of this triangle. Because once we consider the biggest triangle, all points naively belong to inside, included inside. But this is not meaningful. So we want to shrink the volume and try to recover the smallest triangle that contains all data, all training data. And we try to justify this volume minimization approach. And the first case, suppose among endpoints, there are some noiseless labels. We don't know which one is noiseless, but suppose noiseless labels exist. Then actually those noiseless labels are corresponding to these vertices. Then, by shrinking the volume, naturally we can recover the true triangle. That's one justification, simple one. Even without noiseless labels, still we can justify our approach. So as long as our noisy data, training data, is so-called sufficiently scattered. So I don't really have a condition for this in this slide, but we have some mathematical condition. That means points are kind of distributed. Then, in this illustration, we have 2 points on each edge like this. Then, as you can see, if we shrink the volume of the triangle, we can recover the true one, even without having points on vertices. So that's one of the justifications of our approach. So as far as we know, this was already published 4 years ago, but this is still one of the, I think, most powerful approach to make the true noise transition matrix foundation. That was a good conclusion. So we can obtain the noise transition matrix T quite accurately under weaker condition. But the real world noise is unfortunately even more challenging. What we have considered so far was so-called input independent noise. But this means that noise property is essentially the same over the entire domain like this. But in reality, we often have more noise near the boundary because these points are more difficult to label, and other points are easy to label, so we don't make mistakes. Then, if we really want to handle this situation, we need to consider so-called input-dependent noise. And so now we need to consider T of x. So the noise transition matrix is a function of x. Even if T is a constant matrix, its estimation was quite difficult and challenging. But now T of x is a function of x. So it may be not really possible to have a systematic approach to estimating. So we end up in exploring some heuristic solutions, and we had several methods so far. And each of them are somewhat justified in experiments, but still we need some hidden assumptions behind some heuristics. So we can't really guarantee the performance. So that's why we decided not to really follow this approach. And I will come back to this point later, this problem later, because we are nowadays exploring a completely different approach to tackle the same problem. Okay, that was about noisy label learning. Then the third part is transfer learning. This is also a short part. Then, now training and test data follow different distributions. So as I said in the beginning, because of changing environments over time, or because of sample selection bias, because of some privacy reasons. So we have training and test data following different distributions. Then the goal of transfer learning is to train a test domain predictor using training data from different domains. You want to predict test data, test labels from training data coming from different distributions. And this is actually not a new topic. Already we organized actually a workshop almost 20 years ago at NIPS conference. And at that moment, there was no name for this problem. Our workshop name was NIPS workshop on learning when test and training inputs have different distribution. It's really a long workshop name, but this really explains the problem. Then actually we had a lot of great speakers, and after a couple of years, we published a book together with the speakers in the workshop. And at that point, we named this problem dataset shift machine learning. But unfortunately, this name, dataset shift, did not become popular, and it was completely forgotten. But very recently, they have new names. So distribution shift, fine tuning, and so there are actually a series of workshops in NeurIPS from 2021 in now, hopefully this year too. So about distribution shift and fine tuning. So the topics are essentially the same, but we have now, it's rebranded a new name. But still, basic technologies are quite the same. But the surrounding environments are a bit different. Because previously, machine learning systems are trained in this way. So we prepare a small size or medium size model, and we collect medium size data and train the model from scratch. So that was a kind of classic approach. But now we have a pre-trained foundation model. So web scale data was collected, foundation model was prepared. Then, this is fine-tuned based on downstream data. So the paradigm has been changed, but still mathematical techniques are quite common. So that's why this transfer line topic is back again. So then let me quickly review some basics of this transfer line technique. And it uses importance weighting. To illustrate the problem, let's consider the situation called covariance shift. So here, only input distributions change. Like x is input and y is output. And p of x only changes. But p of y given x does not change. It can be illustrated nicely in one-dimensional relation. The input x in the horizontal axis, output y on the vertical axis, and the target function red one does not change, but the input location changes. So we have training data from the left-hand side, but this data from the right-hand side. So from blue point, we want to predict black crosses. So this is a typical covariance problem. It's quite challenging. And if we just naively apply linear least squares, then we end up in having this green line. So we just fit blue point and we obtain this solution. But this green line does not predict black losses at all. Doesn't work well. And we can easily show that. So ordinary training is not consistent. But once we apply so-called the importance weight here to the loss function, then so we can actually recover consistency. So PTE is the test density and PTR is the training density, and we consider the ratio of them. So this is called importance. Then only from blue points, okay, we recover this, we obtain this green line. It predicts black losses quite well, and it is actually consistent. So importance is basically a weight to the loss function, and in this simple example, okay, most of the blue points have zero importance, or almost zero importance. They are thrown away, and only a few points on the right-hand side. But they have larger importance. We basically obtain this green line only from one number of points on the right-hand side, because they are important. So once we know the importance weight, so we can recover the consistency, but we don't know the importance. So we want to estimate it from data. So that was the classic challenge. It's called direct importance estimation. So in this scenario, we use training input points and test input points. Then, so the method called kernel mean matching is quite elegant. So they try to match the means of PTE and RPTR. R is an estimate of the importance weight. And if R is PT over PTR, so PTR is cancelled and these two are the same. So they do this matching in the reproducing kernel Hilbert space. This is called kernel mean matching. It works quite well. Then we also have another method called least-squares importance fitting. So we try to fit the importance model R to the true importance weight by these squares, like this. So this is a bit complicated, but once this square term is expanded and some constant term is ignored, we have like simple expression like this, and they can be estimated from two sets of input data in a consistent way. And the beauty is that so in these two methods, so PTR, PTE, so these densities are not estimated, but only the ratio is directly. We can avoid estimating densities because this is quite difficult. But we can directly estimate the importance weight. Then based on this importance weight estimation technique, so classically we perform two-step adaptation. In the first stage, we estimated importance weight, for example, by least-squares importance fitting, and obtain R hat. Then in the second stage, so second step, so we use this R hat as the importance weight and obtain the final predictor F hat. So this was a kind of state of the art 15 years ago. And actually, I had a lot of industry partners and we explored many applications. And this actually worked quite well 15 years ago. Still, like we know that this is not the best way because of this two-step nature. So when we estimate the importance weight in the first step, we basically ignore the second step. So estimation error in the first step is not taken into account in the second step. So ideally, we want to integrate these two steps to one process and then obtain the solution. So we were aware of this limitation already 15 years ago, but we couldn't really have a good solution in many years. But finally, so 2020 and 2021, so we had good solution. It's a joint optimization technique. So the situation is so-called unsupervised domain adaptation. So we have labeled training data and unlabeled test data. So that's the standard setting. Then instead of estimating the importance weight first, so we first actually have an upper bound of the test risk. I don't really go into the detail. So test risk squared divided by 2 is upper of J function. The J function actually consists of 2 terms. And these 2 terms are actually exactly the same terms appear. So this is quite interesting. So this means that in the previous two-step approach, so this upper bound was minimized in 2 steps. But now, so we have an upper bound. So we directly minimize it jointly with respect to the importance weight R and the final predictor F. And then we can really have consistency and better theoretical properties. And this also works much better. The more recently, so we are extending this importance weighting technique to so-called sequential shift. So far we considered like a training phase and testing phase. But now testing phase can also change over time because news appears, events appears every day. The world is changing over time, and we want to use online learning technique to adapt our model over time. This is because nowadays foundation model is quite big. The retraining system took a lot and takes a lot of time, and it's impossible to update it every day. Then basically fine tuning is only possibility. I call it online learning. So we basically perform online gradient descent, but we have two methods, so both can overcome the changing distribution over class barrier or input density, so covariance. So we have very strong theoretical guarantee that the dynamic regret can be minimized under some conditions. It's a simple online learning technique, but this can be applied to fine-tuning the final layer of foundation. Then finally, so let's merge these three topics and talk about our current challenge. So we did a lot of work on distribution shift, but many distribution shift works actually focus on a particular shift type. For example, our case, covariance, E of X. But actually, identification of the shift type is the most challenging part because our setting is basically unsupervised adaptation. We only observe unlabeled data from the test domain. Then basically, there's no way to identify whether the shift is really covariant shift or not. We only have unlabeled data from the test domain. Also, label noise. So as I said, label noise is a quite challenging problem, but label noise is also a type of distribution shift. So we can regard it as changing P of y given x in the training and test phase. In the training phase, we observe noisy labels by bar. In the test phase, we assume we suppose we have clean label y, observe clean label y, and we want to predict. So PTR and PTE are connected in this way. And in the middle, we have noise transition. Then, as I presented already, so there's a nice theory for input independent noise. So in that case, this X is dropped. Then the noise transition matrix T is a constant. We have a nice theory. But in reality, we need to handle input dependent noise like this. But then, this is still a quite challenging problem. Then, our current approach is to consider so-called the joint shift. So P of X and Y changes. But this covers both two cases. We don't really have to identify the shift type, but just directly train. Then, we did some research on this. So first, if we assume small number of label test data, then actually we can solve that one. But this is a bit contradictory approach because if we have a large number of label test data, then we don't need transfer learning. We can just directly train on label test data. But if there's no label at all, so there's no way to handle joint shift. So here we consider kind of intermediate we assume we have a small number of labels. Then, by applying kernel mean matching in a dynamic way, so we can somehow solve the important in a dynamic way. So that's one solution. So then later on, this approach was extended to out-of-domain problems because often, we want to have. When I introduced covariate shift, I illustrated kind of extrapolation problem. But this is actually not really true because we are considering the importance weight. Then PTR cannot be 0. So this means PTR actually has a wider tail and it covers the entire domain. The PTE is kind of included in the training. So that was a kind of hidden assumption behind. So in this case, actually, we used Gaussian distribution on blue points. Then Gaussian tail actually covers the test region. And black points are also Gaussian, but it's a PT1. Then the importance is always finite. But that's why we could guarantee the consistency. But in reality, we want to really consider extrapolation. But then, we found that by applying some outlier detection technique to split test data into the training part and testing part. And for the training part, we just apply importance weighting. And for the testing part, so they are pure test data. So we just compute the loss by dictionary and just add them up. Then actually we can guarantee consistency. So we have results like that. But still, like with this approach, we need a small number of label test data, and that's a kind of biggest constraint. And we want to overcome this. So our current line of research is try to combine this joint distribution shift approach with weakly supervised learning. At least we have shown that for classification tasks, so we can solve the problem only from weakly labeled data with statistical guarantee. And we are wondering whether like we can apply a similar kind of idea to joint distribution shift. We don't observe pure strong label from the test domain, but we observe only weak label from the test domain. But hope that we can show that this is sufficient to adapt our predictor to the test domain under joint shift assumption. So that's the current ongoing line of research. Then, so this is the final slide. So more future challenges are learning under this changing environment. So now we have common foundation model in society like ChatGPT, and everybody uses it. Or nowadays we personalize it. Like we download it and have a smaller version in our mobile phone and use it. Like I have my own AI system in my own environment and interact with it and update it. Then, as we discussed, so world is changing over time. Then, so my interaction with my AI system is evolving over time. Still, we want to somehow handle it in distribution. This is a kind of natural extension of our learning. So learning in dynamic environment. So topics like online learning, continuing learning, perfect learning, potential decision making. So these are quite important in this scenario. We still need a lot of them. And then, so we have one more important axis. That's the kind of diversity axis. So we have many users. So the system is personalized. So then many users have different, slightly similar but slightly different AI systems. And they are interacting each other and updating. Also, they have many different tasks, and there are also different modalities. So then, so learning in diverse environments. So in this scenario, so we need to think about multi-agent learning, multi-agent interaction type of research, in addition to multimodal learning, multitask learning. Then also we have many systems. Then so privacy preserving, also adversarial learning, fairness aware learning. So these societal topics are quite important. Then so this is a kind of society-wide large system. Then computational efficiency and energy efficiency are quite important. And so naturally, we need to consider large model and big data system, and in a distributed environment. Maybe data could be compressed. And also, we may need some new computing paradigm to handle this beyond GPU. Because nowadays, for GPUs, we need one nuclear power plant to train the system. And this is quite bad. And we want to overcome this issue. So as a machine learning theory person, we may not be able to directly contribute to this field, but still, even still from a algorithmic viewpoint, so we can somehow contribute to the computational efficiency. And it's clear that this computational efficiency can contribute to energy. Hope that we can also contribute to this kind of environmental problem. Okay, so these are our ongoing line of research. Of course, we can't really cover all topics by ourselves. So some of the RICAM members are working on some of these topics, but we need more collaborators together. So hopefully, like today, so we have 2-day workshop from tomorrow, and we can discuss a lot of topics together. So we hope to find collaborators to work on important, interesting challenges. Okay, so thank you very much. Yeah.
Any questions?
So I wish my colleague James Bailey was here. He told me yesterday he has some prior commitment because he is exactly in this space.
Oh yeah.
And so he would have been very interested to hear the talk. So if he's here tomorrow, I will.
Oh, that's great. Thank you very much.
I'm very sorry. So this is not my exact area, but several points you went very quickly. It's a lot of material, so it was hard for me to. I got lost someplace. So I have a small question on slide number 21, I have three slides that I would love to see, but number 21. Oh no. What? No, the way you had the simplex, the triangle, yeah, this one, yeah,
Oh, yeah.
22, I'm sorry. So please help me understand a little bit. If I'm getting all this, I get the points, and I don't know which is true and which is noisy. So I just give, and I can draw them here, all the little white circles. Now, if there is a bias for the edges, as you said, right? If I look at the density, just the density, the proportion of the density, I don't know the proportions, but I know that there's some on the periphery here that seem denser, right?
Yeah.
But there's some outliers and things like that. Could I not make an assumption that I just split them in two? I say, I'm going to look at this, and the ones that seem to me just ugly outliers, I'm putting them there. And the ones then, if my simplex becomes smaller and smaller, I throw him out. Oh, now my simplex is tighter. I throw him out just because I feel like I don't like him, right? And suddenly, boom, boom. Then I come to a point where the densities, the balance of densities is such that that I can have a tighter, as tight as possible simplex. This is, I think, what you're doing is you are doing that right now, because I didn't follow all the mathematics. So picking the ugly one and throwing him out and having a bound on how big I make the ugly one, that's something, it's just a heuristic search, right? It's kind of a clustering, almost search procedure in a search space. What's the complexity of that procedure? Did you look at that sort of complexity?
Okay, so thank you very much for the great question. So your interpretation is really correct. So let me just recapitulate the problem here. So we have noisy data points, and they are distributed in this triangle, right? So by definition. But in this definition, we didn't consider outlier. So noisy labels are still following like noise distribution properly.
Sure.
That was the assumption here. Then by minimizing the volume, we can really recover the true one under these conditions.
But can I not pretend there are some outliers?
Right. So then suppose we have some outliers, then okay, we should be able to ignore some proportion of samples that are outside the triangle.
No, maybe I speak wrong. Can I say if I don't, I should not say outlier, I should say inlier. The ugly ones I don't like are in the middle of the triangle. The good ones I like are on the far points, right? They're the true ones, upward.
Right. In the center, so they are quite
the center
ambiguous.
is my noisy one. I don't like you. So I'm going to look in the center, my inliers, if I want to use that word, right? And I throw it out. I say, I don't like you. You confuse me. Boom. You confuse me. Boom. Now my space gets more settable, more clean.
I see.
And that search space.
In this algorithm, basically points in the center are not really playing any role, because we just shrink the volume and
yes. So
we can safely ignore them.
Yes.
So to improve the computational efficiency, maybe we could get rid of those points. But as a final performance, they don't affect.
So you really look at the boundaries of the simplex.
So yes, I would say.
And you just try to
so
say.
Then, so outliers are more critically, that's not wrong. So we have some points. Thank you very much. So that's really the right interpretation.
It's just, sorry, I'm just slow, but I try to understand it now because you put a lot of stuff in my mind. Yeah.
Thank you very much.
Questions from the audience?
Thanks for a very great talk. So I have a question regarding the adaptation. So I previously also work on unsupervised automatic application.
Yeah.
Right now, with fine tuning, I think most people go with like a supervised fine tuning or error-based fine tuning. Do you think this like an unsupervised adaptation method idea could be used in the fine tuning of the large model?
So a bit for covariate shift and label shift, it is possible, but our assumption is that only the final layer is trained. So feature extraction part is frozen. The final layer comes. So then we can guarantee that the dynamic regret. So this is a supervised adaptation.
Yeah, so you think if you only fine tune the last layers, So this
In
method.
this scenario, yes, to guarantee something.
Okay.
So it's basically linear prediction or online convex optimization. So we just freeze the linear model.
I see. I see.
In the end, the method is quite simple, just online gradient descent.
But this is for theory, right? For theoretical guarantee. If we don't care about the maybe theory, you can still fine tune more layers.
Yes.
Okay. Yeah. Thank you.
So nowadays people use supervised, for fine tuning. So then, of course, we need supervised data. So then that's the final part. So we want to do this weekly supervised way. For one-step learning, already we have a solution as weekly supervised learning. So then we want to somehow extend this scenario to joint distribution over time. The problem is very complicated, but we hope to have a simple online gradient type approach to overcome the problem.
Yeah. But I think in your last slide you showed that for the personalized LLM.
Oh, yeah.
I think for those applications, maybe it's not easy to get to the level from users.
So this is okay, still not mathematically well formulated. It's more like a conceptual illustration.
Okay.
So we have done some research only on this part, but hopefully, like in diverse environment or distributed environment, we want to make it more efficient. Because a lot of models are similar. We just personalize them, but they are coming from the same model originally. There must be a lot of similarities.
Yeah.
Also, some users are quite similar to each other, and we want to take advantage of that kind of property.
Thank you.
Can I ask another
Yeah.
question? On slide 18, with the UU training,
This is an interesting formulation.
yes, on the top left there. Just to see if my understanding is correct, I have two experiments. And in one, I do my experiment, I train with stuff, and now I test. And on the test, what do I get back? I test this example, just calculate the
Right, so test is like a third data set.
Yes.
And then so we can give a label for each test sample.
So on the test feedback, there is a label.
Yeah.
And now I take a second experiment, and again, and on this one, I also test. And I also get that. Now I look at the proportion of the unlabeled test to test, and training to training. And I look at those balances, those relative proportions.
So we have two sets of unlabeled data for training purposes.
Yeah.
Then we can train a classifier. Then later we have a new test point.
Yeah.
And we can give a label of this test point.
Yeah.
So that's the standard scenario.
Yeah.
So then so your case is
Now I have experiment number 2, the second case, and I do again. I take the same training data, but now I test the second time, right? For the second, because you have 2, and there's a different distribution of answers coming back from the 2 experiments.
So, okay, my understanding is, so we have 2 sets of data, and mathematically, actually, one is regarded as noisy positive points, and the other is regarded as noisy negative points. And then together, okay, we can train a classifier in a system, right? So we have 2 sets, but they are like coupled.
Oh, I see. It's in one thing. It's not 2 different experiments. No, okay.
So, okay.
No, I understand.
Okay, they are 2 different experiments, but assumptions are still like class probabilities are the same. So class-wise densities are the same. Input x and output y. We assume P of y is different.
Yes.
P of x given y is the same.
Yeah.
Only proportions are different in 2 experiments.
And that's what you leverage, the proportion difference.
Right.
Okay. Then it goes back to the previous formula with the balancing. Yeah. Thank you. Yeah.
Any questions? I think we can allow one more question. Yeah, I have one question about the PU learning. In PU learning, the most important thing, I think it's the proportion of the positive label is very important.
Right.
Right. So first I talked with Nan about it. I want to know, like in practice, so this one is easy to be estimated, and how the robustness for this estimation. For example, if pi has error like 0.1, 10%, how it will influence the performance in the end.
Right, thank you very much. So estimation pi is actually not that easy. So this is something I completely skipped today. But mathematically, actually, we have a like similar difficulty to estimation of noise transition matrix T. So naively, so estimation of pi is not really possible, but we need some additional assumption.
Yeah.
Then those methods basically take advantage of those additional assumptions or some heuristic. So, right. So then if pi is large, unlabeled data contains mostly positive points, then this is actually quite difficult because we don't really have negative information at all. We have a lot of unlabeled data, but most of them are positive overlap and only a small number of negative data. Then the performance is really bad. In that case, I think so outlier detection is more suitable than PU classification. The outlier detection and PU classification are essentially the same problem. But if pi is not so high, then PU classification is more useful. But if pi is quite large, then outlier detection is more useful.
Thank you. Okay, if no more questions. Let's thank Professor Gale for the break.
Thank you very much.
Have tutoring outside. It's good.
ありがとうございました。お忙しいところ。また引き続きよろしくお願いします。